Welcome to Unit 2, Lesson 3, the derivative. In our last video, we saw that to estimate the slope at a single point, well, we know, for example, that the slope right here at 0 is 0 because it's not going up, it's not going down. If we were to draw a line, we can see that, let's use green, the line's not going anywhere at 0, so the slope is 0. At 1, it started going up, so the slope is positive. In fact, the slope is 1. Here, the slope is higher because it's going up faster, it's steeper. If, for example, we want to figure out the slope at x equals 3, we can use different intervals. For example, we can use the interval x equals 2 to x equals 4. That's this point to this point. And we can find the slope by drawing a straight line in between. The slope of this line is an estimate of the slope at x equals 3. To get closer, we can use, say, x equals 2.5 to x equals 3.5. We would have this point and this point. When we draw a straight line, it will be closer to our real slope at x equals 3. So that's what we did last time. So to estimate the slope at x equals 3, we can use different intervals, say 2 to 4, 2.5 to 3.5, 2.9 to 3.1, 2.99 to 3.01, and so forth. We're getting closer and closer to 3. If here's on the number line, and here is 3, we started at from 2 to 4, and we estimate 3. And then we said, let's get closer. 2.5 to 3.5. To get an even better estimate, we can use 2.9. Let's not use yellow. 2.9 and 3.1. So we said we're getting closer and closer to 3. Okay. Now, there's another way to use intervals. Instead of using 2 to 4, we could just use 3 to 4. That's going to make our algebra a little bit easier. Instead of 2.5 to 3.5, we can go 3 to 3.5. Instead of 2.9 to 3.1, we go 3.3 to 3.1. It's still going to work because we're still going to get closer and closer. Eventually, we're going to get to x equals 3, to x equals 3.0000001, and so forth. So we'll get to x equals 3 eventually. Our limit is the same. We do this because we can write our formula for the derivative this way. Remember that the average rate of change is this. Well, here is our formula again. I'm just going to write this out. So here's our formula. F of x2 minus f of x1 over x2 minus x1. So earlier we have an x1, x2. Maybe the graph is going up like this. So we're looking for these two regions. Instead of x1 and x2, I can change the names. So instead of x1, I'm just going to call this x. Instead of x2, I'm just going to, let's use a different color. Instead of x2, I'm going to call this x plus h. In other words, we have gone from, to go from x1 to x2, we go up by h. So this is x plus h. In other words, x1 becomes x, x2 becomes x plus h. Then our formula would look like this. x2 is x plus h. x let's go back. Sorry, here's our formula again. So we see that x1 becomes x, x2 becomes x plus h. So we can replace this. x2 becomes x plus h. x1 becomes x. And we can do the same thing over here. x2 becomes x plus h. x1 becomes x. Of course, x plus h minus x is just h. So, to summarize, here's another way to write our derivative. F of x2 minus f of x1 over x2 minus x1. You can write it this way. F of x plus h minus f of x over h. That's the same formula. But now we want to take our limit. We know, as we saw earlier, we're going from x, we're getting closer and closer to x equals 3. Remember earlier, if we're trying to get from 3 to 4, this time, instead of calling this x1, calling this x2, I'm just changing it a little bit. I call this x, I call this x plus h. So if x goes from 3 to 4, the interval is 1, because 3 plus 1 is 4. To go from 3 to 3.5, h is 0.5. To go from 3 to 3.1, the h is 0.1. To go from 3 to 3.01, the h is 0.01. H is getting smaller and smaller and smaller. When h gets smaller and smaller and smaller, eventually at the limit, h becomes 0. And when that happens, we're going from x to 3 to x to 3. That's not an interval anymore. That's just a single point. That's our instantaneous rate of change. So we can write this in terms of limits. H is getting smaller and smaller. So this is the same formula, except with the limit of h approaching 0. In other words, slope at a single point or the instantaneous rate of change can be given by this definition. Limit as h approaches 0 of f of x plus h minus f of x divided by h. This is called the derivative. It's one of the two big ideas in calculus. In the next video, you'll be using this formula to help us calculate the derivative. So what is the derivative anyway? The derivative is just the instantaneous rate of change, or the slope, at any single point. Going back to our graph over here of f of x equals 0.5x squared, the derivative of here is 0 because it's not going anywhere. The derivative of the graph here is 1. The derivative of the graph here is 1. The derivative of the graph here is 2 because that's the slope at that point. This is negative because it's coming down. So the derivative of the graph here will be something like negative 2. Okay. So instead of writing the big long formula, we can write f prime of x. That's just another way of writing the derivative. A third way is df over dx. We can write df over dx like this. We can also write it like this. We can write d over dx with an f to the side. Sometimes we can write it like this way. D over dx of f of x. That means the derivative or the slope at a single point. Okay. To help us understand this better, let's look at some examples. So, example 1. The slope of the function f of x equals x squared is equal to 2x for any x. This is true. We'll prove this by applying the definition in the next video. But our question here is to write this in derivative form. So we know that the slope of f of x, that's just the derivative, is x squared. So we can write that df over dx equals 2x. Or we can write d over dx of f equals 2x. Or finally, f prime of x is 2x. Different ways of writing the derivative. Okay. Well, given that this is true, when x is 4, well, f of 4 is given that the derivative is 2x, when x is 4, 2 times 4 is 8, so the slope of f of x is equal to 8. To write this in derivative form, we can just write, the easiest way is to just write f prime of 4 is equal to 8. This means that the derivative of f at x equals 4 is 8. The slope of f at 4 is 8. Or we can write df of 4 over dx is equal to 8. Okay. One more example. This time, example 2. The slope of g of x equals x cubed plus 4x is 3x squared plus 4 for any x. To write this in derivative form, we can just write f prime of x, that's the derivative, is 3x squared plus 4, because we got that here. We can also write df over dx is 3x squared plus 4. Okay. Well, if the slope is 3x squared plus 4, the derivative is 3x squared plus 4. When x is 5, 5 squared is 25, times 3 is 75, plus 4 is 79. So the slope of f of x is 79 when x equals to 5. We want to write this in derivative form. To do that, we can just write f prime of 5 is equal to 79. That's it. Alternatively, you can write d of dx of f at 5 is equal to 79. So when you see this, we know it means that the slope at x equals 5 is 79. This brings us to the last two examples. If a prime of x equals 5x, that means that the slope, the derivative, or the slope of a of x, the function, is equal to 5x at any x. Example 2. b prime of 4 equals to 12. What does this mean? This means that the derivative or the slope of b of x is 12 at the point x equals to 4. That's what that means. Alright, so that's the derivative. In the next video, we'll use the definition to calculate the derivative. That's it.